Hello, everyone. Hope you are listening to me.
Sir,
I'm
Assalamu alaikum, sir.
Salam. Hope I'm audible, right?
Yes, sir.
Okay. So, welcome back to our power plant engineering class. So, today we will try to cover the graph part of the math, which is capacitive probability analysis. In the last class, we have completed that math. So, the graph part we will try to understand today. Okay. So, in your exam, you need to draw that graph. Uh, Maybe you can use normal graph paper, also you can use semi-log graph paper. If not, you can draw it just uh, uh, in a very random page, in a fresh page by hand. But you need to point out every single value, okay? If you just plot it by hand, but if you use the graph, then you don't need to write every single values, but the initial values you need to write it. Okay, so I'm just go through the math very in brief, and then i I will try to cover the graph part. Okay, so in that math, it was like 300 megawatt generation uh, capacity of a particular power plant, and they asked to uh, understand the probability of forced outage and understand the probability of being in running condition of 300 megawatt plant if it is in 1 unit, is in 2 units, 3 units, and 4 units. So to complete the math, we need to understand the equation, which is P plus Q to the power n. For one single power plant, the value is given, uh, which is operation probability is 0.98 and forced outage probability is 0.02. It was given. So after that, we have put equation for 2 unit. Then we find out that the probability of being forced outage for two plant is 0.0004, and it is in operational, which value is shows 0.9604. And like that, we have completed the third part for 3 units. Also, we have calculated these values. The probability of outage is 0.000008, and another. Finally, we have completed this term for 4 plants, 4 units for 75 megawatt, and you found for all the plants are in outage mode, that probability is 0.00000016, which is very, very small. So if you increase the number of units, you will get less probability of forced outage. So like that, now we need to draw the graph. So this is a graph uh, where you see there are two axes, probability of forced outage, and in the x-axis, these are total capacity. Okay, this is capacity. So we can say that x-axis shows you overall 300 megawatt capacity in x-axis. So this is 100, this is 200, this is 300. So if you have one single 300 megawatt unit, that unit shows you the forced outage probability values is 0.02, right? In the first value, it is given. You see Q equal to 0.02. If it is 0.02, your graph should start from 0.02. As there is no other unit, that value should continue up to 300 megawatt. Okay, that is our forced outage probability. And the other part, that is the probability of no loss. That means all the units are in operational mode. That value should be 0.98. That means in left side, this is a semi-log graph, you see, where the y-axis, this is semi-log, and the x-axis is normal. So the y-axis is log graph. So you can find that 10 to the power naught, this value is 10 to the power naught, that means 1. Okay, if I just make it big, so that is 10 to the power naught, that value is 1. So 0.98 should be somewhere around here. Okay, so this graph should start from this point, and the forced outage probability is 0.02. And you see this point is 10 to the power minus 1. This point is 10 to the power minus 2. And 10 to the power minus 2 means 0.001 or 0.01. What is the value of 10 to the minus 2? 1 by 100, right? 0.01. And 10 to the power minus 1 is 0.1, right? Am I right?
Yes,
So
sir.
your probability of for the first one single 300 megawatt unit for forced outage probability, the value is 0.02. Okay, for number forced outage probability 0.02. So this value should be somewhere in between 0.01 to 0.1. So if I just consider this is a logarithmic axis, so maybe that value is somewhere around here, 0.02. So here from this point, you need to draw this up to 300 megawatt, as our x-axis is here, 300 megawatts. Up to this, you need to draw it a constant line. So one single 300 megawatt unit shows you the whole probability of outage is 0.02, and the probability of no loss of the generator, that means they are still operational, that is 0.98, somewhere here. Okay, so this is the first graph, this is the first line. Okay, now for the second plot, I just change the color so you can understand clearly. For second one, the probability of being operational is 0.96 here, this one. That means 0.96 is maybe below this point, so this one. So you need to start from here, and the probability of forced outage value, it shows 0.0004, this one, 0.0004. So we need to write it here, value 0.0004. So that value is very small, so we can write it like that, maybe 0.0004. Okay, so the value should be for two 150 megawatt units. So 150 means this is 100, this is 200, this one here, and 300 means here. So there should be a staircase type of plot which provides you two particular value for this graph. So we might find it here. See, this is 0.02, this point. So you need 0.0004. So 0.0004 should be 10 to the power minus 4. What is the value of 10 to the power minus 4? 0.0001. Am I right? And 10 to the power minus 3 is this point, 0.001. Is it okay? So
Yes.
you see 0.0001, that means this point and 10 to the power minus 4 and 10 to the power minus 3. In between, your 0.0004 should lie, right? So as it is 0.0001, so somewhere in between these 2 points, there should be 0.0004. I am taking this point as 0.0004, maybe. So like that, it will reach up to 0.001. So this point, you can, if you just draw it up to 150, you can cross here. So if you consider this point as 0.0004, so from 300 to up to 150, this line, and you see uh, the value between 0.01 0.1, that value should be this point. Sorry, not this one, this one. The value is 0.03 for 150. This is 0.0392. So that value should be here. 0.0. This is 0.02. So 0.03 should be here on top of that 0.02, 0.03 maybe. So this one is for other 150. So it produce a staircase. That means if you consider your 2 units are down, forced outage, that value is 0.0004. So up to 150 to 300, this line provides that value. And if you consider you have only one 150 megawatt unit, so then this line provides that value. Okay, so for 2 units you are getting 2 outage probability, one for 150 megawatt unit down and another for 2 150 megawatt unit down. So we can write it like that: 150 megawatt unit outage, and here 2 150 megawatt unit outage. So this is the complete graph for 2 150 megawatt unit. Okay, now you can consider 3 100 megawatt unit, the third part of the math. So third part of the math has 3 100 megawatt unit. The value is 0.94. If I take another color, then you can understand it clearly. Suppose this one, 0.0941. 0.94 may be below to that point. This is 0.94. Okay, so from here you can draw the line up to which point? Up to the forced outage probability for 3 power plants is 0.000. Sorry, this is 0.05, right? For one outage, 0.057624, 0.05. So where should be the 0.05? It is 0.03. On top of that, that point should be 0.05. Okay, so starting from here, you should go up to 100. This is our 100 value. Then falls down up to this value, 0.001. So where the 0.001 should be, you need to falls down up to 0.001. So you see, this is your 0.001. So the value is 0.001 something. So it should be higher, up to some higher value. So this is our 0.001, and on top of this is 0.0017, something like that. So falls up to that point, and then again moves up to 100 into 100. That means 200. So here, 2 100 plant. Here it is 100 megawatt, and then up to 200 it should move. Then you need to fall again. So what is the value is 0.008. That means 0.00008. So you should fall this up to this point, 10 to the power minus 5. That means 0.00001. So the value is less than that. So maybe below to this point. This is 0.00008. So draw the line from 100, 200. This value, the graph falls, and then it moves up to 300. 3 100 megawatt unit outage. Done. So this is the third graph. Now the number 4. Number 4 has 475 megawatt unit. So from 0 to 75, the value falls from 0.92 to 0.075. So you should start from 0.92. 92 should be here somewhere below 0.94. So here it should start, and 0.05 on top of that 0.07 should be there. So the value is 0.07. So somewhere here this point should be 0.07. So you should start from this line, and up to 75 you should stop here, and then falls down. Second value, find the second value. Second value is 0.002. So in between 0.001 and 0.01, the value should be there. So this is 0.001 and this is 0.01. So 0.001 and 0.002 may be here. So we can false the line up to here. We can follow that and then again move. So it is our 1 into 75 unit. It is our 2 into 75 unit. And then again, you need to find the third value for third power plane loss, which is 0.003. So it should be somewhere in between this value, 0.00001 and 0.0001. So maybe here it is 0.003.
Sir, HM Zubair Bhai is trying to join. Can you accept it?
Okay, I'm accepting. So this is 2 into 75 and the value is 0.0004, maybe 4 here. So it is up to this. So you need to connect the line up to 0.0004 and the final value is 0.0000016. So it should be 60. That means 0.000001 and that is 0.00001. So in between where maybe the value should be. So you need to draw the line up to 3 into 75 and then you need to draw this up to that point. So here and connect it till 300 megawatt. That is 4 into 75 megawatt unit outage probability. So this is how you need to draw the graph. So you have all the values and you can draw it. If you have fifth unit, suppose I'm considering 560 megawatt unit, I will provide you the math, okay, additionally. So maybe you will get another starting point, maybe somewhere in this line, maybe here. This is maybe it should be less than 0.92. Maybe it will be 0.90. Maybe. So you need to start it from below point, and maybe you will get that outage probability is much higher than the 475 unit. Maybe it should be around 0.1 or 0.1, around close to the 0.1, and you have 560 megawatt unit. You need to divide the whole 300 megawatt in 560 megawatt part. So each of the box is 50. So you need to draw the graph like that, maybe up to this, and maybe you need to draw the next line here. It should be higher than the other values. Then maybe your next line should be somewhere here. Okay. So like that, you need to draw the 5 staircase, right? Maybe like that. Maybe like that, okay? 1, 2, 3, 4, 5 staircase. So like that, if I increase the number of plant unit, you need to calculate further. You need to draw the graph on top of the 4 others, okay? So like that. So I'll provide a complete one set math, one math particularly you need to solve in your exam, and that is one of them. So you need to draw the plot as well. Okay, and mentioning the whole values I have mentioned here like that, and also the unit number and the staircases. Okay, and in your exam, if you just draw it freehand, you should provide all the point values. If you use the graph, then starting and the different graphical representation. That means if you draw one graph is like direct line, another maybe in dotted line, another maybe in dash dot, like that. If you separate it, then you don't need each of the staircase values, just put the primary one. But if you use freehand drawing, then you have to put all the values in the staircases. Okay, that is on complete math, which I have started in the last class, and this is the graph. So if you have any question regarding this graph, you can ask me. So you find from this graph that if you use one single unit, that should be the highest value of being in operation, this one in the top value, red one. So that should be the highest. But if you find the four or more generating plants, you will see the 4 units should the least capacity probability of forced outage, right? So this is the two findings from this graph. Okay, as from the value we can find it out. Any question? If not, then we can move forward. So in the last class, we have covered the capacity probability analysis. Today we'll try to cover another topic, which is called energy rate related problems. So maybe today is lecture 12, I guess. If not, then I think this is a lecture 12. So today we'll cover different types of energy rate. Okay, so what is the objective of using energy rate? Okay, so the main concept is if you just produce power and if you just want to supply the power, the user will utilize this based on their utilization time, and there are several factors you have already covered: utilization factor, plant factor, so many things. So if you use that amount of power for a certain period of time, you are consuming energy, right? So that energy which is supplied from the generation side, they are basically selling, they're trying to sell that energy, right, to you, and industry or other consumer consumes that energy, and that energy for producing that energy you need to utilize fuel, you need to maintain your plan, you need to provide salary to the operators or engineers, right? And definitely you should buy so many things related to the power plant, and those things should carry a much more tax. Okay, so overall every single unit you are consuming, that should carry a price. So that's why you need to design that price from your supplier end. So if you want to sell a power, suppose 5 taka per unit, and one particular power plant is providing you 4.5 taka per unit, definitely you want to buy the power from another 4.5 per unit company, right? Or the provider. So also, if you have one particular industry, the load of that industry should be inductive. So that type of industry should have separate rate rather than from the household owner, right? If you have one apartment, you don't want to pay a big amount of price, but if you have industry, you can pay that amount of price, and you have different types of machineries, so maybe the price should be different. So according to those different load demand and different varieties of those load, the energy rate should be different for different from different utilities, right? So that's why you need to design that rate. So that's the main objective of designing the rate. So that electrical energy, that cost actually is of 3 types, like cost of installation of plant. So you can, if you just write it down, so electrical energy cost, is of 3 types. Number 1, fixed cost, plant installation, so if you install that plant, it should have a very big amount of price, fixed cost. So if you produce energy, fuel, you need to burn, and that is called energy cost. That can vary from season to season, time to time. So that is variable cost. We can say energy production. So another type of cost is charges, right? If you want to supply that power, you need to fix a charge, because you need to maintain your grid, maintain your substation, you need to maintain your plant, and also the service provider should have so many employees, so those should have some supply charges, right? So these are the main things you need to consider. So what are the types of fixed cost? You are saying plant installation, so there are so many types of fixed cost. Like for plant, you need to consider if you want to install a plant, you need to consider so many things, like land. So land should have some cost. Maybe you need to design some building, right? Building should have some cost. Maybe you need to purchase or hire some equipments to build that whole power plant. You need to set those instrument installation cost, should design and planning cost, right? And also if you consider like the T&D, transmission distribution, and also the substation, which I mentioned, right? And maybe there are some government taxes, VAT, interest, whatever. So it's like that. The employee salary, maybe you can say managerial or management related cost, right? Etc. So many costs are related to plant installation. If you consider energy, so energy should have some other type of cost like fuel cost. We will cover one math from this part, fuel cost. And labor, we have covered one particular economic plot in the last class that provides you some concept regarding the per unit cost versus labor cost versus total cost, right? So labor cost should be there. And also you need to buy some supplies regularly, like maybe for boiler, for maybe for the turbine. Okay, so you need to consider so many things for that particular cost, and also some lubrication for, if you consider diesel generation, lube oil, right? You need, and maybe water treatment plant, you require some chemical, okay, etc. These are for energy cost, and you need to consider supply charge. Supply charges, actually it covers maintenance cost, for maintenance for line, transmission line, okay, substation, etc. And also you need to set up meters, and also for office, you need to manage some office, right? DESCO office, DPDC office, you need to manage those things. And also you need to publicize. That means media coverage, publicity, etc. So many costs are there. Okay, so these are this covers actually supply charge. So considering those things, general rate is considered to design these energy rates, which is also called tariff. Okay. So any question? Any question from your side?
No, sir.
Okay. So now we need to understand what is the general form of this energy rate or tariff. Okay. What is the general form of tariff? So general form of tariff, it requires some parameters. So we can write the equation considering different derivatives. So the equation is dx plus ez plus c. So where y is total amount of bill for a period, so this amount of bill is that is actually, you are getting that value or that amount of bill for energy consumption. So you are consuming energy, right, for a particular time, for a particular period, and for that you are getting that total amount of bill. So from where this bill is coming? From D. D is for unit charge. Okay, the meter you are setting, that unit charge. So that is also, suppose if you consider BDT, the unit should be BDT per kilowatt hour. If you consider maximum demand, so BDT per kilowatt, that is your per kilowatt you need to pay. That value is your unit charge, and total amount of bill, that is in BDT. The unit is only taka, BDT, maybe 5,000 taka. That is your bill for that particular month. So X should be your maximum demand during that period of time. So for that January month, you have maximum demand of something, that is X. So X is your maximum demand during billing period. And finally, you have E. E is your unit charge for consumed energy, okay? You know energy is kilowatt hour, so it should be, suppose BDT per kilowatt hour. For that energy, you need to pay some money, right? And you have Z. Z is total consumed energy, okay? Total energy consumed during that period, which is kilowatt hour, only kilowatt hour. And the C, that is your constant, that means service charge, okay? We can say constant charge. Or service charge. So you see, you are considering three types of things. You are considering the cost for fixed cost, which is installation, and for power plant, that cost maybe it is considering the demand, maximum demand related, which is dx. That is your plant cost, okay? You can say this is our fixed cost. So variable costs are energy consumed, right? So energy cost, this is our, we can say energy cost. And final one is our cost of service. Three types of costs. If you consider, then you can write the equation like that. Y equal to dx plus Ez plus C. You understand? So any question?
No, sir.
So what are the types of tariff then? So there are so many types of tariff. So for design, considering so many limitations and other things, so I just write some of the names here, but we cannot cover that much of things. I will try to provide you 2 or 3 tariff rate, and you can go through others. So types of tariffs, there are so many types. First one is flat demand rate. I'm just writing the name first, then I'll go through some of them. First one is flat demand rate. Okay, flat demand rate, that is a pretty simple method of charging energy. So maybe you have some maximum demand, you have maybe the total cost. You can just simply consider that, okay, 5 taka per energy. That's it. That is flat demand. No other consideration is here. Okay. Just a second. I have to take a call. Sorry for the interruption. Anyway, so we are considering flat demand rate. The flat demand rate, it is actually basically a very simple demand rate. There is no other equipment related, service related, no cost is there. Simply, if you have the total energy, if you consider the maximum demand, you can get the value, very straight line type of graph. Okay. So as this is not actually practically used so far, so it's based upon the old fashioned, maybe in the previous 1800, 1802. In that time, they use street light, right? For that street light, they have the fixed demand rate. So, and they choose to design the tariff using flat demand rate. Okay, so graph should be like that, flat demand rate graph, and the equation should be y equal to, as you know, we have general rate dx, maximum demand is your x, and d is your rate. So your equation should be y equal to dx. So if you consider the graph should be like that. So that is your y, which is your total cost. So z is the maximum total energy supplied, you can say. And if your demand is x1 demand, so your rate should be this one, flat rate, maybe 5 taka per energy. If you have demand 2, that means maybe you need the demand 2 kilowatt. Previously it was 1 kilowatt, you have the rate some taka per energy, maybe 5 taka per energy. If you have the demand 2 kilowatt, maybe it is 10 taka per kilowatt energy. If you have the maximum demand maybe 3 kilowatt, then it should be maybe 15 taka per kilowatt hour energy. So as you see, if you have the increasing demand for your house, you are not using that, right? You have the 5 kilowatt of load in your house. Do you think you are using 5 kilowatt load for a particular day? Is it really a realistic thing? No, I think you are using maybe very small amount of energy for today. Maybe it varies from day to day. So according to your utilization or use, you should pay. But here you cannot do that. You have the maximum demand for your house, 5 kilowatt, you should pay for 5 kilowatt each of the month. But you are not using that. So that is why that flat demand rate is not valid. Okay? Is it clear to you? Or if you have any question, you can ask. Just stop. I'll stop and answer. Okay? Any question?
স্যার আরেকবার একটু রিপিট করা যাবে?
Anyway, so flat demand rate, I'm just talking about. Suppose you have a house, you design your house load for 5 kilowatt. If you just pay every month 5 kilowatt hour energy consume, you are each hour you are using 5 kilowatt consume energy, so you have a very high amount of bill considering the flat demand rate. Because if you have 5 kilowatt load, maybe your bill should be 15 taka per kilowatt hour energy. So each hour you are producing 15 taka without considering you are turning on the light or not. Okay, if you are using the load or not using the load, you need to pay that. So considering that thing, the demand rate is not justified. It's not like that. If you just consume energy for 1 hour or for 2 hours, maybe you have the demand 5 kilowatt, but you are using maybe 1 kilowatt for that particular hour. Just television or AC you are using, not other loads. Why should you pay for other loads? That's why the flat demand rate is not valid nowadays. Okay.
Okay, sir.
So now you see in our previous equation, the flat demand rate is y equal to dx, the first part. This one, this is our flat demand rate. Now you need to consider the next one, which is called straight meter rate. Okay. Meter rate. So meter is related to the energy consumption. So if you consume energy, the price should rise, right? If your energy consumption is more, your price should be higher. So like that, the meter rate should, it is used like that way. The straight meter rate, it represents the equation y equal to Ez. So Ez means you know E is represented unit energy, maybe 5 taka per kilowatt hour energy, and you are consuming total energy, which is called Z. If you multiply it, you are getting the bill which follows the straight meter rate. Straight meter rate is very simple. Y equal to Ez. So this equation actually a straight line equation. So from that, you can conceptualize that your graph should be straight line. So the graph should be like that for straight meter rate. The graph is like that. So here it is Y, your total bill. Here it is total consumed energy, Z. So as you see, if you consume more energy, your bill should be higher. It is linearly increased. Is not it? This is our straight meter rate. You understand? So you're consuming more energy, and you are getting more price, more. You need to pay more, right? That is our straight meter rate. But the straight meter rate has some issues and some problems. It has, okay. The problem is if you consider that suppose you are consuming more and more energy, initially your energy consumption is very small. Suppose in your house you are not using AC or heavy load, just lights and fans. But if you have the straight meter rate, the rate for using that light and fan for a particular small home owner and the rate for a very big apartment owner who is using AC and other things, it is not considerable that you are paying the same amount, because you don't have the same types of load, right? One is using heavy amount of inductive load, one is using very straight resistive load, but you are paying in a same rate. In a straight line method, you are paying in the same rate. So that is another issue. So you need to separate that type. That means based on that load type, you need to separate the meter rate. So from that concept, step meter rate is coming into the scenario. So we can put the third rate, which is our step meter rate. Okay, third one. Step meter rate is coming from straight meter rate. So you need separate types of straight line for different types of load. So step meter rate will provide you the information like that. So this is the similar concept, Y equal to Ez, but we are taking Y1 may be equal to E1 Z1, Y2 equal to E2 Z2, maybe like that. Okay, their slope is different. That is the main thing. So graph should be like that. So this is our Z, this is our Y. Suppose for who is using very load, suppose type 1 load, he should pay this, considering this straight line. And another load owner, he may provide the charge considering the second straight line, and another person may provide the charge considering the third straight line. So what will happen then? You can see if you just consider the first plot, first owner consumed A1 or Z1 amount of energy, that is his highest energy. He is very small consumer, so he may pay the price considering Y1 rate. Suppose I'm just considering this. So maybe after that, this should rise here, falls here, and then again he should pay for another Z2 amount of energy considering the second straight line, and maybe it falls from this point to there in the third straight line. And if he continues to pay the bill for the higher energy rate, he may follow the third line. Considering the third line, he can pay the bill. So that is called stepping your demand, okay? Stepping your rate of that meter. Okay?
Yes, sir.
Yes, sir.
So the concept is you need to separate your load consumer. Suppose who is consume high amount of load, he should pay one type of price, and low consumer, he should pay different type of price. That concept is called step meter. And if you consider this step meter, there is another disadvantages. So what is the disadvantages of using a step meter rate? So the disadvantage is, you see, if you consider Z1 and Z2 consumer, suppose you are talking about Z2 consumer. Z2 consumer, first he needs to consume Z1. So if you consume Z1, you see in certain point, in Z1 point, the price somehow reduces, and then he should pay another Z2 amount of price. This reduction is the disadvantage. We are not reducing the price, rather we want that he will again pay some amount after this range. That should not decrease, that should increase, right? So we cannot reduce any type of price. We don't want it. Rather we want to increase the price. So here, rather considering this is increasing, we should make it flat, make it constant up to the next level. Then he should pay again linearly, he should pay more, but before going to the next level, the price should constant. This type of some arrangement should be there, rather decreasing the thing. So that is called modified step rate, modified step meter rate. Okay, so we can change the graph. So the graph should be like that, similar graph of the previous one, but we need to flatten the decreasing point. So maybe this is our first plot. Rather decreasing the plot, we can draw in the flattening. Rather decreasing this, we can flatten it from this point to this point. And again for the third one, we can make it flat here, rather decreasing it. Okay, we may decrease it, but it will be our step meter rate, but it will flow. It will provide you some disadvantage that rate is decreasing in some Z1 point. So we don't want it. We want from this point he should pay constantly, and after the second rate, after that point, he will pay more. So this is our modified step meter rate, and you see there is no price decreasing in any point. Okay. So you understand this part? Any question?
No, sir.
So the general rate adjustment that is coming from which is called Henry. So this general form of rate is introduced. It is introduced by Henry. That's why sometimes it is called Doherty rate. Okay? Doherty rate. Sometimes it is called Doherty rate, and that Doherty rate, it is also called three-part tariff. As you see, the first one is flat demand rate. The next one is step. We can say step meter rate or state meter rate, whatever. And third one is our constant, or we can say service charge. So it has three parts. So sometimes this general form of tariff is called three-part tariff. Okay, sometimes it is called three-part tariff. So that Doherty rate or the three-part tariff, the final part of our type, different rate type, and which is called Doherty rate. There are so many other rates, but I will stop here. Doherty rate. So Doherty rate, the graph or equation is dx plus ez plus c. So what should be the graph then? The graph should be like that. So the same thing here should be the total demand. Here should be the price per energy. So if you have one constant C, right? This is our C. The constant should be drawn here, the constant charge. That is our C. And other part, maybe dx plus ez. You see, dx is for your demand. So if you consider that your rate is actually dx plus ez, so you need to draw or combine these two rate. So you have the dx, that is your straight line, this one dx, and you need to consider ez. Ez is modified ez. That means the third one, this step rate, right? So considering that two graph, if you just combine that two graph, you have one constant c. On top of that, you have the flat demand rate, which is your dx maybe, and after that you have, this is your dx. You see, considering y and z, it should be dx, and ez should be this one, the modified tariff. So if I draw the top part, so it should have three types of slope. So considering that graph, we can draw it like that. So you see, we have one constant. So after that, we can draw the graph. So from this point, we can draw it. This one, then it is flattened. Then this one, then it is again flattened, and this one, right? We can draw this like that. But as you see, this straight line is very small. Sometimes we can ignore that straight line. Rather, we can draw it. Suppose from this point, we can connect it to the other point. So this point to, we can like connect it here. So we can draw it like that. So it should produce you some another slope. And again, we can draw it like that, this type. So the final graph should be like, this is z, y, this is constant, this is our dx, this is our dx part, demand, flat demand, and now we can draw it like that. This, and this. So if you have multiple type of maximum demand, you can draw like that. So this one is for X1 demand maximum, X2. If you have more demand, X3, the rate will be higher. So this is our Doherty rate or 3-part tariff. Okay. Okay, clear? So these are the rate. So how to solve particular math for this rate design? I'll provide you one example for a step meter rate, and considering the step meter rate, you can design your bill. If you want to use another rate, you can use another rate for design. In the final exam, there will be no specific question that you need to design by using that rate. Rather, the question will be set like that: you need to design considering different conditions. You can use any type of rate design, a rate design method. You understand? So, for example, I am providing you example for a step meter rate. Okay. For step meter rate, question is like that. I hope you can see my screen, right? Yeah.
Yes, sir.
Suppose if you use 0 to 10 kilowatt hour energy, the price is 10 cent, or we can say 10 PDT per energy. If you use 10 to 50 kilowatt hour energy, the price is 8 taka per energy. If you use 50 to 100, so the price is less. Price is less than the previous one. The higher the energy, price should be less. And for 100, the price is 5 PDT per kilowatt hour. Okay, so that is the pricing. It is provided from the supplier end. So you need to design the rate. Okay, so how to design the rate into the modified step meter rate? Okay, you need to design it in modified step meter rate. So you see, so for considering these are our steps 0 to 10, 10 to 50, and 50 to 100, over 100. You see, for 10, the price is 8 taka per kilowatt hour. Here also for 10, it is 10 taka per kilowatt hour. The less amount of value is 10 taka for 8 taka for 10 kilowatt hour. So we can design like that. We can make some steps in between there. So 10 into 8 is 0.80 BDT. So for here it is 50, and previously it is 50 for 8 taka. Now it is 50 for 6 taka. So it is overlapping. So we can take the minimum value 50 into 6, 3 BDT. This is our 6 BDT. Okay, 8 into 10, that is our, okay, we can take it not BDT, we can take it 10 paisa, okay, or that we can say it's cents, then it will make sense. So 0.80 and 0.3 BDT. Okay, these are cents, or we can say paisa, whatever. And finally, it is over 100. So 100 is for 6, also 100 is for 5. We can take the lower one. So 100 into 0.5 cents. So it is our 5 BDT. So you see, so each of the step has another value of pricing. We can now set the upper end of the constant for each of the step. Suppose for 50, it is 10 taka. So we can write it 50 divided by the upper end of each constant. So it is 80, not the 50. Right? So 80 BDT divided by 10. So it is here, it is 8 kilowatt hour. So here we can say the over 100. So that is 300 divided by 8. As here it is 0.8, 0.8 into 10, 80. Okay. So 80 divided by 10 taka. So that is 8 kilowatt hour. We have 3, so that means 3 into 100. This is 100 for 3. So 300 divided by price is 8, this one. So it is 37 kilowatt hour. And finally, the 100 into 5. So this 5 is over 100. That means 500. Divided by price is 5, this one. So we are getting maybe 80, 82 or 83 something. Okay. So this is the value of upper step. So 8, 37 and 83. So now we can design the overall pricing, or in between this price, there should have some multiple steps. So we can write like that. For 0 to 8 unit or kilowatt hour, the price is 10 cents per kilowatt hour. So if the first
Second bit 3 into 100 by 6.
3 into 100 by 3 into 100 by 6. Which one? Oh, this one. No, this should be 8. Okay, the top value. Okay, previous one, upper end. We are considering the upper end. This upper end and this one. Okay, and this value should be 6, I guess. No, I think. This should be 6. Sorry, this one is wrong. This is not the upper one. This should be 6. Yes. The 10, 8, 6. You see, the 10, 8, and 6. The upper end of the price. For this one, the upper end is 10. For this one, upper end is 50, and for the last one, upper end is 100. So price should be 10, 8, 6. We need to divide it, and so the final rate, you see, 0 to 8, 0 to 10, it was 10 cents, but we find it that we need to take 8 kilowatt hour. The energy should be 8 kilowatt hour. So we rather taking 0 to 10, we are taking 0 to 8 for 10 cents. And for 8 to 10, that particular 2 kilowatt hour energy, that is our step meter rate. So that step will follow the modified rate. That is our 0.8 cent. Previously it was 10 cent. Now it is, we can say 80 cents, right? It is 80 cents, 0.80 BDT. Yeah. Now for 10 to 37. So that particular is 8 cent. Previously it was 10 to 50, right? now it is 10 to 37, and from 38, or we can say from 37 to 50, it was only $3. You see, 3 BDT or $3, whatever, 3. And for further, it is from 50 to 83. It was 83, yes. So 50 to 83 kilowatt hour. The rate is revised. Previous rate was 6. So 50 to 83, it was 6, and from 83 to 100. So that is revised up to 5. This one, 5 BDT. So this is 5, and the final one over 100, that is previously include 5. So here we see this is our, for these two energy, this price is very constant, because as you see, $10 each energy, 8 into 10, that is 80 cents. So for this 2 kilowatt hour energy, the price is constant. So that is 80 cents. So if for this 2 kilowatt energy, you need to price, you have to pay more. Or considering the previous energy, the rate should be flat, because previously it was 8 into 10, 80. For this 2 kilowatt energy, you need to pay with in that fixed rate. For 10 to 37, it is 88 cents. So 10 to 37, the rate 8 cents. 37 to 50, the rate is total $3, 3 USD, but 3 BDT, whatever we can say. If it is Paisa, it is BDT. So because 8 into 37, if you multiply it, the rate is 3. So for 37 to 50, you need to pay in a constant rate. That is our $3. Each of the energy, you need to pay the constant rate. And for 50 to 83, the rate is previously designed 6. But for 83 to 100, if you consider the 6 cents, for 83 energy, it is almost $5, 5 USD, 5 BDT, or whatever, if you consider. So after 83, you need to pay a flat rate. And over 100, you need to pay 5 cents. Yes.
Sorry to interrupt, sir. I have a presentation at 2.
You can leave, yes. Yes.
Okay, sir.
So this is the final graph. If I just, as it is a step meter rate, starting from 0 to 8. So from 0 to 8, maybe this is the first one, 0 to 8. Then 8 to 10, that is fixed, right? This is our kilowatt hour. This is 10. The rate is fixed. This is maybe 80. After that, it is 10 to 37 per 8 cent. So the graph is following another straight line, maybe this one, and it is up to 37. So this value is maybe 37, and then it is flat line up to 50, and then up above 50, it is 50 to 83, 6 cents. Maybe it follows another straight line. So then it is 83, and after 83, it should be constant up to 100 in a fixed rate. Maybe this is 100, and then over 100, it should be another rate. So over 100, it should be another rate. So if you consider this plot, if you draw the straight line for each of the lines, you can get different straight lines. So this is our final step meter rate. So like that, you need to design. Okay. So that's all for today. So this is mostly a theoretical lecture. We will cover more maths in the next class. Okay. So I'm taking the attendance now. So Tahmidur Rahman